Hello and welcome to the presentation with the title Performance of Support Vector Regression in Correcting Ultra-Wideband Ranging Measurements under Line of Sight and Non-Line of Sight Conditions. My name is Dr. Michael and I'm a PhD student at the Technical University of Graz. Ultra-wideband transceivers allow for very accurate distance estimation, and therefore they have found a way into consumer products. They will be used in seamless access systems, and already now they are used for indoor localization systems to track assets. Ultra-wideband transceivers achieve this by using a very high bandwidth for communication and therefore being able to send very short pulses. Here on the right side, you can see a transmitter and a receiver, and the transmitter is sending such a short pulse, which is then received by the receiver but quite distorted. What you can see here on the receiver side, the yellow part here comes from the direct path component, and in this case is also the first path component. Then the later parts here are the multipath components, which come from reflections of the walls. What can happen is that if there is an object partially or fully occluding the direct path component, then one of the multipath components might forcibly be identified as the first path component. And since the first path component is used to calculate the time of flight and therefore the distance between two radio modules, this will lead to an error. And because of this, there is the need for a method that can detect and also in the best case can mitigate these problems. Of course, there exist several approaches. Among them are deep neural or neural networks, but in this work we want to approach an SVR-based mitigation method, which was first introduced by Marano et al. We evaluate this approach under three different conditions, namely the line of sight condition, where no obstacles are in between two transmitters, then non-line of sight conditions, where big objects like in this case a concrete wall are in between two radio modules, and then what we call weak line of sight conditions, where comparably small objects are between two radio modules. Our contributions are that we evaluate the SVR-based mitigation approach on off-the-shelf devices. We also specifically evaluate what we call weak line of sight conditions, and we benchmark this approach for different feature sets, and also we put our data set online. We evaluate the performance of three methods. There is the detection method, where we use a SVC classifier, and that predicts the condition, so line of sight or non-line of sight conditions of unseen measurement samples. And how we do this, we first split our data set in a training and test set. Then from the so-called channel impulse response, we extract features and manually add a class label, namely line of sight or non-line of sight. Then we train a SVC classifier, and this one is afterwards used to predict the class label of unseen test data. For the mitigation approach, we use a support vector regression machine, and here again features are extracted from the channel impulse response, but this time instead of class labels we supply the distance error, and this is used to train an SVR-based model. Afterwards, during the evaluation, we let the SVR model predict the distance error of unseen measurements, and this distance error is then used to correct the distance of the measurement. For the detection and mitigation approach, this distance correction is only applied if the sample was previously identified as non-line of sight condition. To evaluate these approaches, we first performed a huge data collection campaign where we used the DVM 1001 dev modules to collect data in over 700 different settings, and for each of the settings we collected 50 measurements. What we recorded is the true distance and the estimated distance, and from that we were able to calculate the error. And here on the right side you can see the error distribution of the line of sight, weak line of sight and non-line of sight cases, and here it is evident that the line of sight cases are actually quite good, followed by the weak line of sight, and the worst are the non-line of sight cases. What we also record is the channel impulse response that can be extracted from the radio modules. And this channel impulse response resembles basically the channel between the two radio modules. And what you can see here, for example, is the first path component, which is quite strong, and then some multipath components. From that channel impulse response, we extract 9 features, and these features are used in the for the classifier and for the support vector regression machine. The experimental results are as following. Here in these 4 pictures, one can see the blue lines that are the uncorrected distance errors for each of the 3 different conditions. Then the orange line is the distance error after applying the mitigation only strategy. And what is evident here is that the line of sight condition is worsened by this strategy, while for the weak line of sight and the non-line of sight cases, the error is actually reduced. Then the green line is the detection and mitigation method, and here we can see that for the line of sight cases, this method yields result that is almost as good as the uncorrected values, but still for the weak line of sight and non-line of sight cases, it is able to reduce the error of the uncorrected values. The overall results show that the detection and mitigation method performs the best. And here also for these plots, we used all 9 features. And in these situations, we were able to reduce the residual root mean square error for the non-line of sight cases by about 60 centimeters and for the weak line of sight cases by about 15 centimeters. We also evaluated the prediction accuracy of the SVR method in terms of the R2 score. And here one would mean that it can perfectly predict the distance error, which is of course not possible. 0 would mean that it cannot predict it at all. And here we have a value of 0.2 for the non-line of sight cases and 0.3 for the weak line of sight cases, meaning that there is some dynamic in the distance error estimation. And that means that, for example, for non-line of sight conditions, the SVR does not simply predict always the same value, but there is some dynamic in these estimations. Another issue that we observed in our evaluation was that the estimated distance error is subject to some fluctuations, even under the same measurement settings. And here on the right side we can see 2 pictures. In total we have 4 different measurement settings with their 50 measurement samples. And we can see the true distance, and we can see the uncorrected distance estimate, the true distance, and the mitigated distance estimate or the corrected distance estimate. For these 2 settings, we can see that the SVR is able to reduce the error. Still, there are some fluctuations. In these 2 settings, we can see that the mitigated distance has quite some strong fluctuations. And for example, if we only take one measurement and want to correct it, we may end up with an error that is in absolute terms almost or even bigger than for the uncorrected measurements. So what we observed is that this variation is a little bit stronger for the non-line of sight compared to the weak line of sight cases, and further research must identify features that influence these fluctuations the most, and we hope if we remove them from our feature set, then these fluctuations may also be reduced, but this has to be investigated in the future. So as a summary, we evaluated SVR-based mitigation error approaches. We achieved the best results with the detection and mitigation method, where we enabled all features. In our paper, we have a table with analysis of how well different feature sets perform. So please have a look for more details about the features in our paper. We put our data set online available. And if you have questions, you can, I'm happy to answer them now, or you can also send me an email. Thank you for your attention.